Here's what you've learned so far. Modern science depends very heavily on large-scale computing techniques, whether we look at physics or biology or chemistry or economics or anything else. To perform large-scale computing, we need to use clusters and supercomputers, which are composed of many different conventional computers that together offer a large amount of concurrency. But the downside to this is whenever you have a large amount of concurrency, you have a large number of failures. So we have to figure out how to design our systems and our workloads to tolerate those failures, and that's the essential challenge. What we're going to do through the rest of this course is understand those fundamental challenges through a variety of different software systems and techniques. And so here's a preview of what you're going to learn in the rest of this course. The first thing is we're going to study distributed batch systems. Now, a distributed batch system is the software that manages all the compute nodes in a cluster. And you can think of it almost as like the operating system for a cluster. Now, like any good operating system, it insulates the end user from the details of how things happen. So the distributed batch system sits in front of a cluster and gives the user a simple interface through which they can submit jobs, query their status, and retrieve the results. And that makes it relatively easy for the users. But the distributed batch system itself has a relatively complicated job in that it has to take all the users' jobs, schedule them across the nodes, dispatch and run the jobs, and then return the results to the user. And as we saw in the previous lecture, when you have users coming and going and failures happening, the situation can get complicated very quickly. Next, we're going to look at how to analyze the performance of a large workload submitted to a batch system. Unfortunately, you can't just take a large amount of work and throw it at a batch system and expect to get spectacular performance right away. Instead, there's a lot of different things that affect the performance of your workload. The number of jobs you submit, the number of files that you access, how long they run, how we partition everything. There are many different knobs to turn. And so we have to know what are the fundamental trade-offs in performance and how to analyze them. So we're going to look at things like how do we define job lifetime from beginning to end? How do we analyze good put and bad put? We'll look at Amdahl's law, which gives an upper bound on the performance of any parallel program. And we'll look at the relationship between partitioning, utilization, and load balancing. Now, once you know how to use a batch system and analyze its performance, sometimes you want to create larger complex structures. Maybe you have one job that depends on another. Maybe you want to run thousands of related jobs. Well, if you have complex dependencies, this whole graph of things is known as a workflow. And a workflow describes the whole set of work that you're trying to accomplish. And in fact, we have specialized systems to manage workflows. So if you have a large number of jobs that you can arrange in a graph structure, this is a sort of high-level programming language that you can pass off to a workload manager. And then the workload manager dispatches work bit by bit to the batch system, which then schedules it. Now, to do this successfully requires some careful analysis of concurrency and dependencies in your overall workload. So we'll look at several different languages and options for doing workflows. Now, not all batch applications fit into a workflow model. Sometimes you have an application that has a large number of small and possibly dynamic tasks, which means you may want to be able to create new tasks at runtime after you look at the output of previous tasks. So to do this, we need a different kind of concurrent programming model. And what we're going to look at is a programming model in which you can create and submit tasks as part of a program. So you might have a main program that looks something like this. This is known as a submit-wait programming model, where you have a number of outstanding tasks and you can keep dispatching them as you get results back. So we're going to use this to create applications with massive concurrency, and then we're going to execute them using a master worker pattern. And that's the next lecture. A master worker pattern is a means of dispatching work out to a large number of tasks. So if I have my concurrent program up here at the top, that's going to be submitting tasks and waiting for them to complete. That concurrent program usually gives those tasks to a master, which then communicates with a number of workers and dispatches tasks out to the workers in order to get as many things done as possible. Each worker might potentially run multiple tasks, if it's a multi-core machine, process the results, and send them back. And now the master has some interesting challenges of how to assign tasks to workers and how to deal with failures. The next thing we're going to look at are networks and data movement. So if we're going to use multiple machines, it's not enough to send a computation over there. We also have to send the data that we want to use as well. And networks in large clusters and supercomputers can be rather complicated. So what you're going to learn in the networking section are the basic components of network infrastructure and the protocols that we use to move data around. You'll learn some common tools and systems, and we'll understand how to evaluate the performance of data movement, especially across wide area networks. Now, it's not enough to move data. We also need to be able to store it. So whenever we have a large cluster, we also have a specialized system for storing and managing large amounts of data. So what you'll learn in this section is you'll learn the elements of storage from the bottom up. We'll look at blocks and files and objects, and then study distributed file systems like NFS and AFS, as well as parallel file systems used to get very high performance in large clusters. And we'll look at cost and performance trade-offs in those systems. Finally, we'll conclude with some issues in debugging and troubleshooting. Whenever you have thousands of machines and things can go wrong, it's surprisingly hard to debug because you just can't stop the system all at once in order to diagnose your problems. So to do this, we need different kinds of techniques for debugging. And this involves isolating systems to find deterministic bugs, monitoring techniques in order to find non-deterministic bugs, and tools that allow us to compare environments and other things to detect incompatibilities. So that's a quick overview of the course. Come back next time for the lecture on distributed batch systems.